Good day. Let's talk about direct current motors. We'll be talking about a bit of animation of a DC motor, and then what is counter electromotive force, so back EMF it's called, mechanical power and torque, speed of rotation and armature speed control, shunt, series and compound motors. Those are different types of DC motors, and motor starting, reversing and stopping. What are the special techniques needed there? So let's move on. Um, Now, direct current motors, uh, the main purpose is to transform electrical energy into mechanical energy. That's what a motor does. And all DC motors use a similar rotor with brushes and a commutator, which is present in a generator as well. But only permanent magnet DC motors have permanent magnets on the stator producing air gap flux. And the stators of these other types of DC motors use windings instead of the permanent magnets on the stator to produce the air gap flux. And the basic principle of operation is still the same. So you got the types of shunt wound, series wound and compound wound when it comes to wound DC motors. Now this is the animation. There is a bit of text. I'll just go through the text also, but if you just look here, this is a PMDC motor obviously. So you got the permanent magnets here producing the air gap flux, and then these are the brushes. So as you could see, through the commutator segments you supply different windings, different poles of the armature in different occasions. So when a pole moves closer to the uh, top of the stator pole, it it is magnetized in opposite polarity. Let's say north. In this one is, if it is this, if this is a north pole, this is polarized south, so that it attracts, and so on. It goes like this. The DC motor consists of two components, stator and rotor. The stator is the stationary outside part of a motor. The rotor is the inner part which rotates. In the motor animations, red represents a magnet or winding with a north polarization, while green represents a magnet or winding with a south polarization. Opposite red and green polarities attracts. That's the simple principle of operation. The state of a permanent magnet DC motor is composed of two or more permanent magnet pole pieces. The rotor is composed of windings which are connected in a mechanical commutator. In this case, the rotor has three pole pairs. The opposite polarities of the energized winding and the stator magnet attract, and the rotor will rotate until it is aligned with the stator. Just as the rotor reaches alignment, the brushes move across the commutator contacts and energize the next winding. So that is how the movement continues. In the animation, the commutator contacts are brown and the brushes are dark gray. A yellow spark shows when the brushes switch to the next winding. And let's move on. What is counter electromotive force? A DC machine can operate as a motor or a generator. So the same thing, if you use a prime mover to rotate the motor shaft, then you operate it as a generator. As armature resistance is low, a large amount of current will flow in the armature when the switch will be closed. That is, in the very beginning when the armature is stationary. It has a very low resistance, so just as you switch on, there will be a large current. A force will be produced that's subjected to produce powerful torque, causing the armature to be rotated. So just as you switch on, there will be high current. That high current goes in the armature conductors. when high current goes in the armature conductors, the air gap flux, because of that there will be a high force exerted on the conductors, armature conductors, which will create a high torque, and the shaft will start rotating. Then what happens? When the armature of a DC motor rotates under the influence of the driving torque, the armature conductors move through the magnetic field and the EMF is induced in them as generator. So this is the same as what happens in a generator, because what we have now is a conductor moving inside the electric field carrying a current. No matter if it is carrying a current or not, there will be a voltage induced in the armature. The induced EMF acts in opposite direction to the applied voltage and is known as back EMF or the counter EMF. The it's usually we denote it as E naught. The E naught is proportional to the speed of rotation n of the motor and to the flux phi per pole. Therefore, we can write E naught as Zn phi divided by 60, where n is in RPM again. We continue with counter EMF. So because it acts against the source voltage ES, after we start the motion of the motor, the net voltage in the armature now is equal to the supply voltage minus the back EMF. So if you look at the electrical circuit, E naught appears here, ES is here the terminal voltage. So the net voltage between the input of the armature and the outside terminals will be ES minus E naught. The resulting armature current therefore is ES minus E naught divided by R, where R is the armature resistance. When the motor is at rest, the induced voltage is 0. So in the beginning there is no back EMF, and the starting current therefore will be the full supply voltage divided by armature resistance. That is why we said it is higher, but running current in the armature is lower than that. Mechanical power. The electrical power PA supplied to the armature is equal to the supply voltage multiplied by the armature current, obviously. So that is what is going in. Supply voltage is E naught plus I times R, where R is the armature resistance. Now PA, the power in the armature, therefore is E naught plus IR multiplied by I. E naught times I plus I squared R. The I squared R term represents the heat dissipated. So this is the loss and this is the effective power. Represents the heat dissipated in the armature. E naught I is the electrical power that is converted into mechanical power. So this is the power that is converted into mechanical power. Remember, out of this we will be discussing it later. Out of this also we will lose a small amount at the bearings. Torque. The mechanical power P is given by P is equal to NT divided by 9.55, which is the same as E times I, E naught times I, because that's the power going into the system, which is the same as Zn phi I divided by 60. So combining all that, we could write the torque as equal to Z phi I divided by 6.28. So these factors is a combination of these two, 9.55 and 60. And N, remember, is always in this textbook is in RPM. That's why we end up with these conversion factors. Speed of rotation. When the DC motor drives a load between no load and full load, the IR drop due to the armature resistance is always small compared to the supply voltage ES. Hence, counter EMF E naught is almost equal to ES. So that probably makes it easier for us to do a bit of more calculations. E naught is equal to ES. It's taken like that here, is equal to Z in phi divided by 60. Therefore, N is equal to 60 ES divided by Z phi. So the speed of motor is directly proportional to the armature supply voltage and inversely proportional to the flux per pole. That is what this equation tells us. How can we control the armature speed? Armature speed control. If the flux per pole phi is kept constant, the speed depends only upon the armature voltage ES. So one way to do it is to keep the flux per pole constant and then change the armature voltage. Other methods of speed controls. We got Ward-Leonard speed control system, which is a very standard method used in industry, and also rheostat speed control. How could we do this? Now, Ward-Leonard speed control system, in practice, ES can be varied by connecting the motor armature M to a separately excited variable voltage DC generator. There shouldn't be a bullet point here, sorry about that. Now what we have done here is there is a generator, separately excited DC generator, and this DC generator is run by a three-phase motor, and the generator output is connected to the motor, and motor has a separate field. So this is the motor to be controlled. Field excitation of the motor is kept constant. So this one is never changed. This kept constant. Generator excitation IX can be varied. This one can be varied 0 to it could be increased from 0 to maximum in both directions, positive or negative, depending on which the motor will change the rotational direction. Generator output ES can also be varied. This one can also be varied 0 to maximum, positive to negative. Consequently, the motor speed can be varied from 0 to maximum in either direction, because this output can be varied by changing the field. That's how the Ward-Leonard system works. Now, rheostat or armature speed control. What is that? That's simple. What you do is you got the shunt field of the machine. The current in the rheostat produces a voltage drop which subtract from the fixed source voltage ES, yielding a smaller supply voltage across the armature. So this is the supply voltage which supplies, in this case, both the shunt field and also the armature winding. So when you have the rheostat, by changing the rheostat position, you can easily control the current going into the armature, but the field current will be constant. It is only recommended for small motors because a lot of power and heat is wasted in the rheostat and the overall efficiency is low. Here the armature current, if the current is high, there will be a very high resistive drop or the heat here due to resistive voltage drop. So it's not a good system for high power motors. That's why people use the Ward-Leonard system for high power applications. Now the field speed control based on the field. If the armature voltage is kept constant, the speed of a DC motor can be varied by varying the field flux. That's the other way of doing it. The motor speed is inversely proportional to the field flux phi. So that's the equation which governs it. N is equal to 60 times ES divided by Z phi. This method of speed control is frequently used when the motor has to run above its rated speed. So if you want to go for higher speeds than the rated speed, then you drop the flux a bit, then the back EMF will not become equal to the supply voltage, so that you get a bit more armature current, so that you still can operate the machine at a higher speed, called the base speed, rated speed, or called the base speed. So this is the arrangement. You got the supply voltage both supplying the shunt field and the armature. So the rheostat is now in the shunt winding, in series with the shunt winding. So you just change this one, will change the field current and the field flux. Therefore, now comes the shunt motor. Now in shunt wound motor, field winding is connected in parallel with the armature. Field winding is connected in parallel with the armature. Shunt field current is relatively smaller compared with the armature current. So shunt field is current is smaller compared to the armature current. We do it by, as in case of the shunt generator, you have a thinner winding but high resistance and so on. Starting a shunt motor. How can you start a shunt motor? The tricky thing is, when you apply the full voltage, what will happen is it could burn the armature, because there will be a very high current flowing and there is no back EMF. That's the trick. Damaging the commutator and brushes due to heavy sparking, overloading the feeder, snapping off the shaft due to mechanical shock. The sudden shock can even snap off the shaft, rotor shaft. Damaging the driven equipment because of the sudden mechanical hammer blow. So if the motor shaft is connected to some kind of a load, that load can also get affected. So what do we do? This is one way of doing it. It's called the faceplate starter. What you do is, there are a couple of resistances connected in series and there are some contact points, and this is the arm which is used to start the motor. What you do is, you connect the supply with a resistance in series, so that the armature will have a lesser current in the beginning. By that way you initiate the rotation. Once the rotation is up, you get the back EMF, so the current will drop and the acceleration will gradually drop. When it reaches a certain level of speed, you move the arm from first one to the other. That means you drop off one resistance. Then you got a lesser resistance in the armature circuit, which means you increase the armature current by one more step, and the armature picks up more speed. Then you move from here to here, the third setting, and it goes like that. And finally you connect it directly without any series resistors. So that's the manual faceplate starter for a shunt motor. Then we come to the series motor. In series wound motor, field winding is connected in series with the armature, and the current passing through the series winding is the same as the armature current. Just like, it's the opposite of the series generator. Series motor, speed control and applications. How could we control the speed? You place a low resistance in parallel with the series winding. Remember, in parallel with the series winding, then the field current becomes smaller than before, and the flux drops and speed increases. So this low resistance can also be varied. It could be a rheostat. Applications: any equipment requiring high starting torque or drive devices which must run at high speed at light loads or traction purposes such as electric trains. This is good. And the compound motor. Now two field winding, one connected in parallel with the armature and the other in series with it. When the shunt field winding directly connected across the armature terminals, it's called the short shunt. Remember our discussion on the short shunt and long shunt generators. Cumulative compound motor, where the MMF of the two fields add, just like our discussion before. And the differential compound motor, series field opposes the shunt field. Total MMF decreases with increasing load. So these different configurations are for different applications. How could we reverse the direction of rotation in a compound motor? Now what you should do is, now this is, if this is the way you are operating in one configuration, original connections of a compound motor, that's A. Reversing the armature connections to reverse the direction of rotation, that's one way of doing it. You just flip this one. That's one way of doing it. Or reversing the field connections to reverse the direction of rotation is C. So you keep the armature connection the same, but you flip the two field windings, series field and the shunt field. By that way also you could change the direction of rotation. How can you stop a motor? There are different techniques. One is dynamic braking, because you just cannot turn off the supply and wait. If you do that for a very large motor with high inertia, it could sometimes take days or hours for the system to slow down. It's not possible. You need to stop the system within reasonable time. To do that, when you use dynamic braking, this is what you do. Now this is when the system is operating. Then when you move the arms, the motor gets disconnected from the supply, and then you put it to the right contacts so that the armature is connected now to a load. The motor is now connected to a load. What happens then? You still have the back EMF acting in the same direction. So then suddenly the motor starts working just like a generator, right? The current will still be in the same current direction, has to change because earlier ES was larger, the supply voltage was larger than the back EMF, so the motor was receiving current. But now there is no more ES acting on the armature terminals, but E naught is acting in this direction. So earlier current came into E naught, whereas there is no current coming in now. So E naught, the back EMF, will drive a current through R, which means the current is now opposite. That means the torque is in the direction opposite to the rotation of the armature, which means the motor will decelerate. That's what I have said here. When switch is moved to braking position, a reverse current is produced by E naught and hence a reverse torque. R is chosen so that the initial braking current is about twice the rated motor current. The initial braking torque is then twice the nominal torque of the motor. So that's how you size the braking resistor R. You send a higher current in the motor for a shorter period, which is okay because the insulation can withstand that high current, and the system will be decelerated by applying twice the higher torque as the rated torque of the machine. Another way is plugging. Plugging is even faster. What you do is you swap the terminals. Motor can be stopped even more rapidly. Armature current is suddenly reversed by reversing the terminals of the source. So this is the mechanism. You get the terminals in the other way around. Alright, so then that's called plugging. That brings us to the end. So what we discussed here were current EMF or the electromotive force plays a big role in motor operation. That's one thing. And then the speed of rotation can be controlled by changing armature current or field current. And three main types of DC wound motors are shunt, series, and compound motors. Motor starting, reversing, and stopping needs special circuitry, especially when it comes to high power motors. And that's the end of DC motors. Thank you.